policy circles, we often think of the triple helix and how to make the triple helix function in such a way that we can accelerate science. Professor Vidyasagar is a living example of having been in each of the helices. In the government, the triple helix is the academia, government, and industry, and he has actually had stints at all of these three places and has also helped shape activities in these places, further collaborations among these entities, and so on. Some other things about Professor Vidyasagar. He is one of those who has an Erdős number of 2 and an Einstein number of 3. Erdős number, for those that are not familiar with it, is what is your distance in terms of paper authorship to Paul Erdős, the prolific mathematician, and of course a similar distance to Einstein. So his Erdős number is 2 and his Einstein number is 3. He is currently a National Science Chair at IIT Hyderabad. So it's a pleasure to welcome Professor Vidyasagar.
Thank you very much. I think this is on. For those of you wondering, the clock is fast, 5 minutes fast. And some of the older people in the audience like to guess, how did I get an Erdős number of 2? With the common link between me and Erdős. Some of you know the answers, but I'll tell you at the end of the lecture. Okay. So this title is a little bit different from the title I gave to the organizer. I said I'm going to talk about what is called BASA, asynchronous stochastic approximation. Then when I started making my slides, I found that I could finish the whole thing in about 25 minutes. That would leave a huge gap in the lecture. So I added more material. And as you can see, this block asynchronous stochastic approximation has now been relegated to the bottom. And it's now almost like a junior partner in this lecture. And much of the lecture is on non-convex optimization. So thanks to Vivek Borkar, India is kind of the world capital of people specializing in stochastic approximation. So it's a real pleasure for me to be admitted to membership in this very exclusive club. So what is stochastic approximation? So this was introduced in 1951 by Robinson Monroe. And the objective is, in their paper, was for a scalar valued map, but I'll make it vector value. So you have a function f from Rd into Rd, and you want to find the solution to the equation f of theta equal to 0. And so the iterative algorithm we use for doing this is in a current guess, measure the function at that current guess, and add a multiple of that by stepsize, and that gives you a next guess. But the real challenge is you don't have a clean measurement of f. What you actually have is a noise corrupted measurement. Okay? And the question is, when does this converge to the right answer as time goes to infinity? And you'll see later on in my lecture, I'm not interested only in these asymptotic results. I'm also interested in rates of convergence to this solution. So there are 3 types of updating that one can do in the vector case. First, I'll call synchronous stochastic approximation. Here the idea is that at each instant you're updating all the components of your guess p of t. This is not a very standard term. I'll just introduce. Asynchronous stochastic approximation, that is a standard term. What it means is, at each instant of time, you update only one component of theta. And then in between, which is the concept I want to tell you to attend this lecture, is what I call block asynchronous stochastic approximation. Here the idea is that at each instant of time, Salam, is it possible to get some water? Yeah. So at each instant of time, you can choose some but not necessarily all of the components to be updated, and the choice can also be random, can vary from one time instance to the next and so on. Okay, we'll discuss each of these. So A lot of problems in reinforcement learning, as we know, are solutions of fixed point problems. So suppose you have a map G, okay, which you want to, whose fixed point you want to find. So how do we put it into this framework of solving a function 0? Well, you just define f of theta to be g of theta minus theta, and when f is 0, that means you have found a fixed point of g. So what happens to the basic iteration when you do this? Thank you. So now it looks like this. So what happens is that the next guess is a convex combination of the current guess plus a noise corrected measurement of the function g. So problems like temporal difference learning, Q learning are trying to solve fixed point problems, right? Now let's come to non-convex optimization. Here you have a function j, which will make it continuously differentiable, and you want to find a stationary point of the gradient of the function, which means you want to solve the equation that the gradient is equal to 0. So this is essentially the previous framework, except we choose f to be the negative of the gradient. And small quiz, why is there a minus sign in front of the gradient? Anybody want to take a guess? Because if the gradient is 0, then the negative gradient is also 0. So why have I put a minus? Well, it's very simple, and most of the time we're trying to minimize this j. So this is like doing a steepest descent. If you want to maximize, you don't have the minus. So the idea is that you have a search direction at each time. And I don't put the minus sign here, I put the minus sign there. I hope you don't get confused by that. So I'm calling it the search direction, even though it's actually the negative of the search direction. But anyway. So we have a search direction at each time, and we don't assume that it is the gradient. And why do I do that? Because a lot of the progress in non-convex optimization has come from these kinds of methods, like the heavy ball method of Polya, and Nesterov accelerated methods, Adam, or Nesterov. None of them use the gradient as the search direction, right? And the updating is now, you take the current guess, subtract from it some multiple times the search direction. Now at this point, you will say, what happened to the noise? Well, I said that the search direction is corrupted by noise. So the noise is hiding inside the image. Okay? And there are several possible error models, and the most important is the bottom. I don't want a theory that is restricted to convex functions alone. Right? There's enough of that. So let's talk about non-convex optimization. So just some basic idea and notation. Suppose f of t is a filtration. By filtration, I mean an increasing sequence of sigma integrals. And the conditional expectation of some random variable with respect to the sigma f of t is usually denoted by this symbol. I'm going to denote it by that because we never change f anyway. So this notation is useful if you're taking the conditional expectation of the same random variable with a different sigma. But since I don't change the sigma algebra, I don't have to show f. And the conditional variance is defined like this. You take the random variable, subtract its conditional mean or conditional expectation, take the norm squared, and again take the conditional expectation. Now notice that both the conditional mean and the conditional variance are themselves random variables. So here's a new concept. It actually came from stability theory. And the last time I was in the institute, I was actually talking about how this concept is really useful. So a function mapping the positive and real to itself is said to belong to class B if it satisfies this condition. You take a small epsilon, a large m, and you let R be restricted to this interval epsilon to m, and over that interval, the infimum is always positive. So here's an example. So you see this function, it's 0 at the origin. But so long as R is not actually 0, it is positive. And it is going to 0 at infinity. But so long as R is not actually infinity, it's going to be fast. And there is no assumption that this function has to be continuous. I took a continuous function because I was lazy. But the definition of a class B function doesn't require continuity. Okay. So now I'd like to mention a couple of my collaborators. One is Professor Rajiv Karandikar, who is an emeritus professor at the Chennai Mathematical Institute. And the other person is Uday. He was the topper in electrical engineering from IIT Hyderabad in the 23 graduating class. So he got a scholarship to this PhD at the UPenn. Interestingly, Rajiv and I have papers, Uday and I have papers. We don't have a 3-year paper. Maybe it will change it. So let's talk about a linear recursion. So this is the equation I'm talking about. Theta of t plus 1 equals 1 minus alpha t times theta plus alpha t times the noise term ct plus 1. And you can choose a random initial guess. And the noise is random. And most importantly, step size can also be random. Okay. And especially when you're doing some of these adaptive methods, you have to permit the step size to be random as well. So this is the point I'm making here, that you just look like a simple linear equation, but once you understand the structure of this, you can pretty much solve it. Okay? So let us define f of t to be the sigma algebra generated by the initial condition, the step sizes, and the noise up to time t. Okay. So my assumption, which I'm going to call n, is that there are two sequences of constants, mu for mean and n for magnitude, such that for all t we have almost fully. By the way, everything I say in this talk is almost fully, so I'm not going to keep saying it over and over. It's kind of boring. Okay. So the idea here is that the conditional expectation of the noise at time t is bounded by this constant mu times 1 plus the norm of theta. Okay. And the conditional variance of the noise is bounded by this mt squared into 1 plus norm theta squared. And it's a high school algebra to show that if I have 1 plus theta t squared, you can split it up and absorb it into the two sides. That's why there is no theta t. Okay. Now, just focus on the bottom. This assumption is the most general class of noise signals today. Others had, for example, mu equal to 0, which means you have unbiased measurements. Or MT is bounded by a constant, which means the variance of the measurement error is remaining bounded with time for each 60. We don't make any of those assumptions. And what we can show is that if these three equations hold, the step sizes are square summable. The product of the mu, which is the bound of the conditional variance, times alpha is summable. And mt squared alpha t squared is summable. Then theta is bounded. And norm of theta of t converges to a real valued random variable.
So in your previous slide, you needed writing to 0 mean, is that right?
No. No, that's the whole point. It's not 0 mean. That's exactly what makes this theory very powerful. Okay.
Is the noise isotropic?
Isotropic? Isotropic? No, nothing. That's what I'm saying. It is the most general condition you can imagine. That, see, in some sense, the non-isotropy is kind of hidden here, because if you have two different thetas with the same norm, then the bound on the mean is the same. So
We have something similar to this, but I think the difference you have is perhaps an assumption on the boundedness of the moments.
Yeah.
Okay.
the first and the second moment.
Because
The first moment.
the bias noise and so forth.
Yes. So the bias noise can grow linearly with norm theta. The variance can, the second moment can grow quadratically with norm theta. Okay. And the constants can also be functions of time. Okay. So now, Sanjay, Sandeep, I'm sorry, I'm getting old. Sandeep, the effect of the bias gets noised by that equation. So that's why it gets worked out. So the point is, the first half of the theorem says that if those three equations hold, then the solution is bounded, convex. And the norm of theta converges to a real valued random variable. But that doesn't say anything about theta, because theta itself could be going round and round. It's just a norm that converges to a random variable, and it is path dependent. Right? If in addition you impose the second condition that the step sizes diverge, then the theta actually converges to 0. So now what about the assumptions on the objective function? So let me just, this is the same slide you've seen before, so I can kind of skip it. It's just a reprise as the slide says. So this is so let me just talk with known results. This is a very, very quick summary of known results. A lot more is known, of course. So if you just choose gradient descent without noise, but the function is only convex, not strongly convex, then asymptotically, the steeper descent method will converge at the rate of 1 over t to the minus 1 over t. So what I've done is I've changed coordinates so that the minimizer is the origin and the minimum is also 0. Basically, horizontal change of coordinates and a vertical change of coordinates. And this makes the formulas a bit easier. Now, Nusselt's accelerated method for convex functions will converge quadratically, and no algorithm can achieve a faster rate. All these three bullets are shown in this Nusselt's book. And then if you use the so-called zeroth order method, which means that you approximate the gradient by a first order difference, then there is this paper by Nestor Spoconi, I hope I've said it right, where it converges at t to the minus 1/2. So this class of function, I will just show you the assumption, and in the next slide, I'll discuss the assumption. So the first assumption is the function is continuously differentiable and the gradient is Lipschitz continuous. Okay. Then second assumption is that the norm of the gradient squared is bounded by some constant times j itself. So this is always true for convex functions, okay. But it can be true for non-convex functions too. Second, this is where a third, I should say, this is where that function of class B comes in. The norm of the gradient squared is also bounded below, not by j, which it would be for a strictly convex function, but just by this function C of class B. So it basically means that as theta becomes bigger and bigger, the gradient is actually allowed to go to 0. We don't care. And then the last one, J3 prime, is that the norm of the gradient squared is bounded below by some constant times j of theta. So this is a counterpoint to that. Okay. So let's discuss. The assumption J2, which is that one, that holds for any convex function, but it can also hold for non-convex functions. J3 prime is actually the polar Losa-Wischich. I hope I've said it right. What is it, please?
Polyaklovasievich.
Okay, I'm going to call it PL.
Yeah, we also call it.
Okay, so this is the PL condition, but J3 is strictly weaker, as I'll show you on the next slide. And there are papers in the literature showing that the function that satisfies J1, J2, and J3 prime, I apologize for this typo, that is actually J3 prime, the PL condition. It's called an invex function. So any local minimum is also global minimum. Okay, I hope this talk. So let me look at this example. This bit here is the same class B example I gave a few slides back. So now what I have done is to take the odd extension of this function and then integrate it. So when I integrate it, I get an even function, right? This function satisfies J1, J2, J3, but it doesn't satisfy J3 prime because theta goes to infinity, it kind of flattens out and the gradient approaches 0. So it is not possible for there to exist any constant like this. On the other hand, I can take a function which has as many zigzags as you feel like, provided only that it is bounded above and below by a straight line. The resulting function is going to satisfy J3 prime as well. Okay. So the point really is, this is just a gradient, and you do the odd extension and integration. So the point really is that this kind of function is very general. So what are the convergence theorems? So suppose we'll start with the noisy gradient setup. So the such direction is the true gradient with additive corrupting noise. Now I'm forced to weaken my assumption on the noise. N was my original assumption, this thing here, and I'm going to change it to N prime, which is that the noise actually has zero means. That's what you were asking earlier. So here I have to assume that. I can't handle the more general. And then the variance of the noise is bounded by some constant m squared times 1 plus theta t squared. So the difference between this and that is that you can have variation, but m of t squared is bounded as a function. For this, you get what looks surprisingly like the Robbins-Monroe theorem. If the step sizes are square summable, then the function is bounded and the gradient is also bounded. And if in addition, the step sizes diverge, then j of theta approaches 0 and the gradient of j of theta approaches 0. Now, you would like to have even more, namely that theta itself approaches 0. You can do that with a few more assumptions, but in view of time, I didn't mention those. So you can basically get everything you want for non-convex function, provided they satisfy those assumptions that I mentioned. Now, here comes an interesting point. So let me just jump to the conclusion. I'm saying that these things are of the order of t to the minus lambda, okay, for some lambda. We'll come to this in a bit. But what does this mean, given that these are all random variables? What it means is, if I multiply these things by t to the lambda, it converges to 0 almost surely. Okay? So that's what I mean by the symbol O of t to the minus lambda. So anyway, so suppose you have a function j that satisfies j1, j2, and j3 prime, the stronger condition, and you do the noisy gradient, and the noise is satisfying. Noise is satisfying this more restrictive assumption. Now, what is your favorite step size? Remember, your step sizes have to be square summable, but the summations have to diverge. So how do you achieve that? Well, you take the step sizes to be t raised to some power, and that power basically has to be greater than half and less than 1. So it turns out that you can make these quantities go to 0 at whatever rate you feel like for any lambda less than 1 minus 2c. And you can choose c arbitrarily close to 0. So effectively, you can get O to the t minus lambda for any lambda arbitrarily close to 1. This is not quite the same as capital O with t to the minus 1, but because of technical reasons, this is what you get. Okay, so you get pretty much the same result as the gradient descent, even when you have noisy measurements. In other words, the bound you get for convergence without noise can be achieved with noise as well. Okay. This is the second one, which is convergence with an approximate gradient. So you take the function j, and at the current iteration theta, you perturb it by some vector capital delta in the positive direction and in the negative direction. So you evaluate the function at the two perturbed points and allow for the possibility of some measurement errors. And after subtracting the two quantities, you divide by 2 CE times the size of the perturbation in the ith component. And why 2CT, not CT? Well, because you have got a perturbation of CT in one direction and CT in the other direction. So 2CT is the right thing to do. So what happens with this thing? Well, it sort of looks like a first order approximation in principle, but it actually is going to only do the 0th order. It actually has a bias which is proportional to CT. So now this particular, in the original way back when, if you look, in Robbins Monroe was 51, immediately in 52, Kiefer and Wolfowitz proposed this technique for non-convex optimization. That proof was very messy, but people sort of jumped on the idea. Now, the problem with that is then a person called Bloom, similar to D-dimensional space, except in this case, he had to have 2D function analysis. He was perturbing these coordinates separately. So that is impractical when D is very large. So this particular idea of simultaneous perturbation was proposed by a guy called Spall and sort of rediscovered by Nestrov and Spoponi. So suppose these measurement errors are unbiased and the variance is bounded by this thing. So it turns out that we recover these bounds with these conditions which are called hypothetical problems. People work with Bloom conditions. Because the conditions themselves go back to 1952, long time ago. So the question is not to find new conditions, but to expand the scope of applicability of these conditions. And also the important point is we separate the boundedness and the convergence. So if just these three conditions hold, then the solutions are bounded. If you add this condition, now the solutions converge to 0, both the function and the gradient. Now just take a look at these equations, okay? You want C of t to go to 0, so that you get a better approximation to the gradient, okay? Now if alpha of t is diverging, how can this be finite? Only if C of t is growing fast enough, decaying fast enough to kill this term. But if you make C of t decay too fast, then you've got this 1 over CT squared which blows up. So it's a very subtle balancing act between choosing alpha and C. So there are two things to be adjusted, and here is the rate theorem once again, that both J and norm of J of theta squared are small O of t to the minus lambda. But what is lambda? Well, if the step size is decaying like t to the minus 1 minus phi, and the increment, the perturbation is decaying like t to the minus s, then it has to satisfy these conditions. And this is high school algebra. But the interesting point is, I think, in the next slide, what I will call the optimal choice of parameters. So here the idea is, you choose those parameters to make the rate of convergence, which I call lambda, as close to 1 as possible. And it turns out that the optimal choice is put phi as close to 0 as possible. So let's call it some small number, epsilon. And this is the interesting point, that the optimal increment turns out to be decaying at the rate of t to the minus 1/3. That's the best increment. In other words, in this equation, in theory, you can choose whatever perturbation you want, but if you want to get the fastest conversion, you want C to decay like t to the minus 1/3. And then what you get is convergence are at the rate of t to the minus lambda, but now lambda is only 1 over 3. Not 1 as we had earlier. And where does this difference come from? Because earlier we had noisy gradient. So once you strip away the noise, what you had was the correct gradient. But here you have two sources of error. First is the noise, but even if you strip away the noise, suppose you put these terms equal to 0, you still don't have the true gradient. You have a biased approximation to the gradient. Now, two gentlemen sitting in the audience, Sarabhatnagar and Prashant, they came up with this thing which they called. I don't think they called it multiple measurement SPSA. I couldn't find the name. So if this is not the correct name, my apologies to you. But anyway, I think it was the higher order test. Generalized. Anyway, but I think the idea is correct, which is instead of using just two measurements, which is what Paul suggested, what happens if you choose more than two, like 3, 4, 5, 10, whatever. And then they have a way of fitting the gradients and essentially fitting a Taylor series, which is kind of reminiscent of the Ramakata method. You know, some of the older people in the audience may remember the fourth order Ramakata method. What was the point of that? Well, if all you had was functional evaluation, and you want to mark the first X number of terms in the Taylor series, that's what it means. So what Shalab and Prashant showed is that when you use K plus 1 measurement, and you choose the functions correctly, of course, you choose the locations of the measurements correctly, of course, then the mean decays much faster. Instead of decaying like C to the T, it decays like C to the T raised to the power of T. And because C of T is going to 0, this goes to 0 even faster. So I was curious about, so what is the optimal convergence rate when you use K plus 1 measurement? All you have to do is to go back to this formula, okay? Substitute that in here and optimize. Very basic high school calculation. And if you do that, it turns out that the optimal increment is T to the minus S, where S is now 1 over K plus 2. So if you use 2-point measurement, then 1 over K plus 2 is 1/3. So that was the optimal increment for 2 points. And if you take more points, say S becomes smaller and smaller, which means you take bigger and bigger perturbations. Okay, actually, which is a good thing. And then the rate of convergence now turns out to be lambda less than K over K plus 2. Okay. Now, I should tell you that this is all in their paper. I'm not claiming any credit for originality here. What I am claiming credit for is a very simple derivation by putting it, by noticing this and sticking it into my earlier set. Okay. So in particular, if you choose K equals 2, which means that you have only 3 function evaluations, you can match the rate of T to the minus 1/2 of the Nesterov and Spokonieri paper. And to their credit, they never claimed this was the best possible bomb. So by increasing the number of measurements, they can get arbitrarily fast. But obviously, there is a kind of point of diminishing returns in the sense that, okay, with K equals 2, you get a rate of minus half. With K equals 3, okay, what do you get? You get 3 over 5, which is 0.6. That's kind of slowing down that. If you take K equals 18, you get 18 over 20, which is 0.9. Probably not worth it at that point. Okay. So, but this gives you the framework for analyzing it. Okay, now let me talk about block updating. So, until now, every component had been updated at each time instant. In this paper by Evra and myself, we study the case where some but not all are updated at each time. So at each time instant, there is some subset SFT which are updated. And then in principle, you need to compute the gradient for only those components. Okay. So in theory, your computation is easier when you do block updating. But in practice, this is not so, because if you have, say, a neural network, how do you do gradient computation? You may use something like backpropagation, and it turns out that there really isn't an easy way in backpropagation to compute some but not all components of the game. On the other hand, if you use this one, all you have to do is to take this perturbation vector and set all components equal to 0 except the ones you want to measure, right? So this actually gives you computational savings. That's what I'm saying in the bottom here. When you use approximate gradient, you only compute those components of gradient that you need. So we compared 4 different methods. One is the full coordinate update. Second is you choose single coordinate update. You choose one out of the D components at random and with equal probability and update only that component. Multiple coordinate update is where you sample n different times but with replacement and you update those. But now the point is when you sample with replacement, you could get repetition, no issue, just update it twice. And the fourth one is the Bernoulli update. So for you pick a rate and you sample each component with that rate. If it turns out to be 1, just update that. If it turns out to be 0, you don't. Now, what is special about each of these 4 updating methods? I think you can see it very quickly. The conditional expectation of H under each of these 4 schemes is in fact the true gradient. So that's what makes this there. So we also, for the heck of it, we decided to analyze Polyak heavy ball method. So this is a pure heavy ball method where you update state of t by alpha of t times the gradient with possibly noise and plus some term with memory, mu times theta t minus 1. And why is there no noise here? Well, theta t you know already is the iteration and theta t minus 1 is the previous iteration. So there is no scope for noise here. And if you put mu, the parameter equal to 0, you get back stochastic gradient descent. So everything I'm saying applies to stochastic gradient as well. So now we are back to the more liberal conditions on the noise. Namely, we do allow a bias and we do allow the variance to grow in an unbounded fashion. Okay. And this is our theorem, which is that if you satisfy the standard assumption J1 through J3, not 3 prime, J3, and with any of these updates, provided the standard conditions hold, then the solutions are bounded almost surely. Now, I hope if you remember what was going on, I'm obliged to move the divergence condition here, and all I get in return for that is only boundedness of the iterations. I don't get convergence. And why is that? Well, because I have got only J3, which is the weak assumption. If I strengthen it to J3 prime, which is the PL condition, then you get what you expect, which is that both J of theta and the gradient approach 0. And some numerical examples. So we took a quadratic of order 1,000,000. It's a 100 Hilbert matrices block diagonal, each of dimension 10,000 by 10,000. So very ill-conditioned quadratic form, even though it is quadratic. And then we took this log sum. And then out of the 4 updating methods, we use the Bernoulli, so the easiest one to implement. So if you have only noisy gradients with the signal to noise ratio of 20 dB, which means a noisy measurement, but full coordinate update, the best performing is the RMS Pro at this one. Yeah. And these two, that is a Nesterov accelerated gradient and Adam. So they're clearly a class apart, right? And this one, stochastic heavy ball method, is it's okay, but not that great, right? And somewhat surprisingly, an Adam doesn't do all that well, and stochastic gradient descent also doesn't do that well here. And when you do only 20% sampling, that's what rho means for the Bernoulli updating. You see, I'll summarize in the next slide. With merely noisy gradient, an Adam and perform fine. And even when you sample only 20% of the component, the performance is quite comparable to full update. But now, let's say what happens if you replace noisy gradients by approximate gradient. It's very different. So there is one curve that's running off to infinity almost at once. Okay. And that's actually an Nestrov's accelerated gradient. So there is theoretical analysis to show that even with noisy gradients, Nestrov's method will still work. So this shows that if you don't use, so noisy gradient means true gradient plus noise. But if you use approximate gradient, it doesn't seem to work at all. And now suddenly there's a role reversal taking place because with approximate gradient, a heavy ball is the fastest converging one. Approximate gradient, I mean this thing.
Small.
This thing.
But then you can still write it out as the sum of gradient and some noise.
Yeah, but the point is that the noise now has unbounded variance. And that's what seems to mess up Nusselt's method. See, if you have noisy gradient, but the noise has bounded variance, Nusselt's method seems to be tolerant to that. If you write it out as the real answer plus variance, then the variance is proportional to 1 over C squared, which is unbounded, because C is equal to 0. So that's what seems to mess up Nusselt's. Have I answered your question? We'll finish the numerical example. Okay. Now, finally, I come to my original topic in the next 7-8 minutes. So let me talk about convergence analysis. Now, here we decide, this is by Rajiv and myself, we decided to study a very general class of what looks like a fixed point storm. So, if we took a function h, which maps n cross RD to the power of n. So RD to the power of n is the set of all possible sequences, right? And the map h is also allowed to depend on the time itself. So h is not actually one function, it's a family of functions indexed by time. You see that? It is non-anticipative, and it also has a finite memory. So what it means is that at time t, the function h, evaluated on this entire infinite sequence theta 0 infinity, depends only on the values of theta from t minus delta plus 1 up to time t. And this dependence is a contraction in the L infinity norm. Okay, that's what this says. Now, you know very well that in problems like Q learning, you have to find a fixed point of a map which is a contraction but in L infinity norm, not L2 norm. So that causes a whole bunch of technical difficulties. We just try to capture this in a more general setting. So because of this contractiveness assumption, if you take any initial sequence and if you keep iterating, it converges to a unique fixed point pi star. Okay, and it doesn't matter what the initial sequence is. So the question is, how do you find pi star when only noisy measurements of which are available? This is really just an abstract version of Q learning. Yeah.
What do you mean by non-anticipative?
Huh?
What do you mean by non-anticipative?
Non-anticipative means that h of t applied to the entire sequence depends only on theta from 0 to t. That would be a non-anticipative map. But I'm actually making it more restrictive, non-anticipative with finite memory. So it doesn't even go more than t minus delta plus. That's what I'm saying. So the update scheme is exactly what you think it is, except it's a bit more messy because you can update some component but not others. So the way I capture that is to introduce this notion of the Hadamard product. If you take two vectors of same dimension, the Hadamard product is just a component-wise product. So I have got what is called the update vector. It's just a d-dimensional binary vector. And alpha of t is a d-dimensional step size vector. So what this means is, if kappa, the particular component of kappa is 1, then irrespective of the, then that component gets updated. If the component of kappa is 0, then irrespective of what the step size is, that component does not get updated, right? And this is the measurement noise. And eta is just a shorthand notation for the measurement. Again, you can go through the paper, you will find that this is just the old Q learning framework in a much more abstract setting. So here, I want to just spend 1 minute talking about this. Our noise measurements and the assumptions on our noise are a little different from what I had before. It looks more like my original N, not the weakened version, but because I'm allowing dependence on the entire past history, if I take the Euclidean norm of theta of 0t, the tail grows longer and longer, the norm gets bigger and bigger. So that won't work too well. So what you have to do instead is to take the infinity norm of this vector, because then even if the tail gets longer and longer, this is still quite well behaved. Now, this is a very important distinction in block updating. This distinction was first made by the way about 1998, so that's 5 years ago. So for each of the coordinates, you define what may be called the counter process. That is, for a fixed index I, you just add up how many times that coordinate equals 1. And then I'm just going to come back to this bit in a minute, so let's just focus on that. You start with a deterministic sequence of step sizes. So at a particular time instant, if the counter process equals 1 and a global clock is used, then the step size for that coordinate is the global clock beta. But if you use a local clock, then the step size equals this fixed constant beta, but evaluated not at the true time t, but the current counter time. How many times have you updated to that? Okay. So implicit in this is the possibility that when you have local clock and multivariable, different components can get updated with different step sizes. But with the global clock, it can't happen. Either it's getting updated with the same step size or it's not getting updated. Now let me come back to this. I introduced this thing called nu inverse. Nu inverse is just a way of inversing the summation. You can read this as well as I can, so I won't take time to go through it. So the only assumption we make about the update process is, essentially this is equivalent to saying every coordinate is updated infinitely often. That's all it's saying. But a little bit more formal fashion, which is that the ratio between the counter process, that thing there, and the time itself approaches some constant r sub I, which just can depend on the index I, as t goes to infinity. And again, this is in probability or almost sure, right? Okay. So now the theorems become very easy. If the local clock is used, so because of the fact that we're doing asynchronous updating, meaning some components only get updated, some components may not, you have to deal with a lot of these delicate issues. So we have to add one more assumption. We permit bias measurement, but the bias has to decrease with time. Okay. Now this is not the true bias, this is the upper bound for the bias. So, but that just has to decrease with time. And then the variance has to be uniformly bounded. And then this part I'm not going to go through because it looks exactly the same as what you have seen before. The distance between the solution and the fixed point which you're trying to find decays like tau to the power of minus gamma. Now what is tau? Tau is the number of times that the updating has taken place. Okay? And if you use a global clock, what happens is, if you use a global clock, we get rid of these two, they're gone. But instead we have to replace by the assumption that the step size is decreasing. And by the way, step size being decreasing is not a very serious assumption because it only has to be eventually decreasing. You know, in all the asymptotic analysis, the first finite number of steps it can do whatever it wants. All you are saying is that eventually it starts decreasing, which I think is fairly reasonable. So then once again, you have the same rate of convergence. So let me talk about the application of Q-learning, and I think I'm going to finish well in time. So what happens in traditional Q-learning theorems is, the convergence theorems require you to verify a condition like this. Namely, for each state action pair, if you take the step size, but count only the number of occasions when that particular state action pair is updated. that sum still has to diverge. Now the point is how to verify something. Because remember, Q learning is a feedback mechanism. So you don't exactly have an easy way of verifying this. So what people assume was, okay, we can get around the problem by saying in a Markov decision process that every policy results in a very decisive Markov process. Every policy. Remember, if a decision problem has n states and n action, the number of policies is m raised to the power of n, so ridiculously large number. So you may say, well, maybe I can still check this condition. Then we found this other paper by John Sickley saying that, well, that is, he didn't tackle that problem. He just said, verifying whether every policy results in a unit chain. What is a unit chain? It's a Markov process in which you have some transient state, but whatever is left over is irreducible. Okay? So he showed that this problem is NP hard. So probably that is also NP hard, but we were not interested. We were just saying, can we get an easier condition to verify? So we introduced this thing called batch queue learning, and batch queue learning is really just n different processes running in parallel. And the point is that in the kth process, you always choose the action to be the kth action variable. And if you look at this thing, this is just a standard, standard queue learning algorithm, except that now I have k different, I have m different processes running in parallel. I won't bore you with all the reading. You know the formulas for it. But the key point is this final result. That, and okay, this is just the definition of local and global clock. So the theorem is very simple. If each matrix A of UK, that means for each fixed action, not for each fixed policy, but each fixed action, the state transition matrix is irreducible, then you get convergence provided you have the standard Robbins-Monroe condition, namely that the structure is a square summable and divergent. So if a local clock is used, you get almost sure convergence. If you use a global clock, you have to add this extra assumption that beta t is non-increasing. So let me just spend 2 slides on what are some good problems for future research. So our method is really based on extending the so-called Robin-Sigmund almost supermodification theorem in a number of different ways. So this is not the end, it's only the beginning. You can actually analyze many other algorithms using the same approach. And our methods can readily apply to block updating, which is not always true of other methods. So Uday and I analyze the Polyak heavy ball algorithm. Others have analyzed Adam using Robin-Sigmund, but only with full coordinate update. So I think a kind of a good topic for PhD students is analyzing all the standard algorithms for non-convex optimization using this Robin-Sigmund theorem, but with or without block updating. I think it's an interesting area. And then this is something that I'm stuck on. What happens when we use Markovian sum? That means the coordinate to be chosen that we are updating is coming from a sample path of a Markov process. I don't have a handle on that because I can't do the suitable error model. So here are some reprints, and so thank you.
Thank you very much. We're now open for questions.
Yeah.
Gugan, maybe you can go first.
Yes, so in convex optimization, is strongly convex case. There have been some papers which say that these momentum-based methods, like this heavy ball and so, they can, whatever performance you can get via them can be obtained by the gradient descent. So, do you think that, and hence some sophisticated momentum techniques have been proposed in the strongly convex case, but in the non-convex case, do you think these simple methods like heavy ball can actually lead to some
Well, I mean, I don't have a theoretical analysis, but if you look at those graphs I showed you, the worst performing was always gradient descent. That's the one which is very creeping down. Okay.
But
Now,
in those works, it is said that if you change the step size of your stochastic gradient descent, then it can show performance similar to those obtained by your momentum-based method, especially the simple heavy ball type.
no, I think that is true. I think that the model seems to be that when you have a strongly convex objective function, all these momentum-based methods don't seem to help you very much. Because even the Spainol gradient gives you exponential convergence, right? So it could be that the heavy ball and those kinds of methods are good only when you have non-convex or convex but not strongly convex, something like that. And similarly, another question, if I may mention, I should have put it on my bullet. I have not touched polar report averaging at all. That also seems to help. But I don't yet have a really good theoretical analysis. That's something under very good problem. Shall I get a question?
Yeah, so in terms of analysis, how different is analyzing asynchronous update algorithm as opposed to block update?
Oh, block is asynchronous is a special case of block. So it isn't very different, just as worse notation. But the point is that if you have a million variables, you're never going to do asynchronous. It will take you the known age of the universe, right? So you have to.
No, but that's a natural thing to do when it comes to online RL. Right?
Yeah.
So sample, so there's a state and you update the component.
So, okay, let me give you your question. Does the analysis pose extra difficulties? Is that your question? It's pretty much the same.
I have a question. So you had mentioned that the subsets that are being updated,
They can be
S
random.
of t,
Yeah.
it can be random.
Yeah.
And you had several choices, but
Yeah.
all of them had this updating comparably often. That is, they would satisfy
Yeah.
Borker's horrible condition. Is that some? I didn't see such a requirement in your theorems, though.
Yeah. So the point is that all those updating methods give you an unbiased system. So that's another problem I'm working on. For example, what happens if you pick a component, but it's not uniform? Then you get a biased estimate. So, but that doesn't matter because my theory is oblivious to bias. Okay. So if you sample in a way that eventually it looks like uniform, that should be good enough. So I think that put it this way, so many permutations and combinations that are worth exploring. So my hope is that there should be some of these people can just follow through all these openings and clean up the area totally. Yeah, sure.
Yeah, so the convergence rate results are asking for or is it like holding for MVP?
No, that's yet one other thing, which is that you want the actual finite time estimate. See, the is a trade-off. If you want it to hold for every t, then the concept in front becomes unreasonably large. So you have to say something like, for all t greater than some capital T, then it's fine. So I have worked on that, but I think that that's a very, very promising area. This might be a person, that's where I think the Polar robot method is going to be better.
Yeah, because the eigenvalue difference did not come out.
That's right. Yeah.
The second thing I want to ask is, even before getting to finite in, have you tried central limit theorems? Like I said, one by n or 1 by 3 and all that, right? Probably in principle, one can write out central limit theorem.
Yeah, I mean, people like Walker and Stallman and writing this central limit theorem type things. I don't think that those methods will survive if you don't do full coordinate.
No, I'm saying just to test the convergence rate.
So I'm saying that
Like
for the full coordinate update, I agree that central limit theorem that operates are very. But the minute you go for block updating, they were set up as us. I don't think that theory will survive. I think it will just go away. That's my feeling.
Thank you very much. I think we'll have to go to the next speaker. I think Professor Vidyasagar will be around. You can ask during the break. We'll now go to the next one. Let's thank Professor Vidyasagar. You have a memento. So we have an IISc Press book called Genomic Quirks. And this is a topic that Professor Vidyasagar has worked on. I'm sure he'll enjoy that book.
I'm sure.
Then another coffee mug.
Okay. Okay, thank you very much. Yeah, I mentioned, I thought that I won't be leaving around 9:30, but if you want to ask a question, I can come up. Or you can visit the next week if you problem. But investment of your time.
Yeah.
So I apologize for having to give you.
Our next speaker is Volkan Jevher. I'll request him to perhaps tell the name once again. We'll call him VC.
Call me Volkan. Live long and prosper.
So Volkan is a faculty member at EPFL Lausanne. He's also a fellow of the IEEE. He has several best paper awards to his credit. And he's going to speak about imitation learning, infinite horizon imitation learning. Over to you, Volkan.
All right, thank you. So, I guess we ordered the speakers this afternoon with respect to their address number. I'm free. So this is joint work with a lot of people. So Luca, my star PhD student, Angeliki, or my postdocs, Gabriel, our collaborators, Igor, one of my PhDs, and Steffi, one of my postdocs. All right, so we'll begin with a warm-up on reinforcement learning. So people know about reinforcement learning. Yeah, I would say it's like an acquired taste, like whiskey or having kids, because any little subtle differences or little progress gives you joy. It's in this topic. But I must also admit that there's a little bit of an entry barrier, which is typically the notation. So I'll give you a brief notation exposure, and then we're going to go full on because I guess only my plenaries can be the bird plenary. This will be a frog plenary. So we're going to be talking about RL, the MDPs, that has state action, transition dynamics, P, reward, initial distribution mu, and the reward, sorry, the discount factor. We're going to be interested in finding policies that kind of map the states into actions. We have the state value function, or just value function in short, which will be the discounted rewards given the initial distribution of the state. And there are many challenges in the setting. Typically, the model-free setting is more interesting, exciting, though EEs kind of have a good handle on the model-based one. And of course, the large state and action space is another challenge. But we're not going to be talking about RL. We're going to be talking about maybe learning from demonstrations, which is somewhat related to RL. So the reward function, when you have the value definition, is central, right? If you have it, if you have a transition model, it becomes more or less like an optimization problem that you can apply gradient methods that can, handle bias or not, and so on and so forth, can be solved. But in many cases, imitation might be the only way. So what I mean by that is that I wish, for example, when I was learning to drive, I had like a counter that would show me a numerical reward. Every time I do an action, I get a reward so that I can optimize my steps. Right? But oftentimes what happens is that you learn by doing. And this is a very important setting. So just to explain the nuances in RL, we have a reward function. We try to find an optimal policy. there is an inverse reinforcement learning where we actually have some demonstrations from an expert that we think is a good expert. And our objective is to figure out their reward function, right? But we'll be interested in the imitation learning setting where we will have expert demonstrations, and we're going to try to imitate the expert's policy. So here, we're going to assume that we have some demonstrations. We do not know what the true reward is, and we're going to assume that the transition model is unknown. So we're going to focus on this imitation learning setting towards an expert policy, and we've done, for some shameless plug, we've done some IRL reward identifiability conditions work with some applications to finance, which might be of interest to some of you. Okay. Now, for the imitation learning, what we're going to do is we're going to take a linear programming approach, which views the RL in terms of a linear program. And I think that this is actually quite nice because it brings the optimization perspective. It puts it in a more prominent position where we can apply some ideas from optimization. So I have two parts of this talk. In the first part, we're going to apply what's known as the proximal point method to solve the LPs for this imitation learning problem. So we're going to discover our algorithm, P squared IL, and there will be a second part where we're going to try to relax the assumption, one of the assumptions that we have. Okay, so a bit of a detour. We are, after all, in a lecture hall, and I apologize, I'm going to lecture slightly. So what we're going to do is just to set up the notation and the basic framework, I'm going to go on a detour on RL first. So given a policy, we have a value function corresponding to it, but what we're interested in some policy space, we're trying to maximize this value function for all S, right? And we get the V star optimal value function. And what we're going to do is we're going to write that as a feasibility problem, right? It seems silly to write it this way, but hopefully you'll see. So what we're interested in is finding a value function that satisfies the downward optimality equation, which is defined by this operator T, where you take the reward as a function of state of action, and then you apply the transition dynamics to go to the next state, and then you weigh the value of the next state, and then what you do is you end up having, let's say, in matrix notation, some states and actions, right? Then what you do is for each of these states, you pick the action that gives you the maximum value, let's say in that row. And then you're going to end up with a nice vector V. All right. And you can iteratively apply to this. So this T, this operator, which encodes this whole expression that I just put here, it's called the Bellman operator. And here, the only feasible assignment that satisfies this as a fixed point is the optimal value function. Right? And just notice that there is a maximization over A, and hence the constraints are nonlinear. Yeah. Now, of course, the Bellman operator has certain properties. So if you end up just applying and reapplying, you have this nice contractive mapping and some monotonic ordering when you apply it to, let's say, ordered value functions. In fact, I think that in the previous presentation, you can view what was being done when applied to Q learning is like a Krasnoselski monitoration with the operator being somehow the Bellman operator or something like this. Okay, now what do? What we do is basically, given that the update takes a maximum over all A, as opposed to taking the maximum, just write down all these equations. Then you end up having these linear inequalities for all state and actions. This is called the Bellman inequality.
And if you think about it, V being feasible has to satisfy all these inequalities, right? Even the one that is the minimum. And hence, what you end up doing is that you try to find, so given this linear constraints, you try to find the lowest speed, and this is very counterintuitive, that satisfies these equations. In fact, in terms of the feasibility equations, one thing you can show, so maybe I should have used my iPad, but let's use our imagination. The constraints are typically have this angle which doesn't, for example, go down in this axis or go in this way, just because you don't want to, for example, increase the value in one and decrease the value in the other one. And you can use the stack to come up with this very simple linear program where you can take any positive weighting of the weights and minimize, and this will literally give you the optimal value function. Right? You exploit the geometry there a little bit. Okay, so the problem is quite interesting. So you take any distribution here, you take the weighting, and then you write down the inequalities, or it's a problem that you can solve. The number of decision variables is S. Say it again.
Why do you want to do it?
I mean,
That's what you do.
so we made a notational mistake. I ended up calling this dual. I'm going to stick with it. So the dual will be the primal will be the dual. And if you think about it, you know, what's primal or dual between friends? You know, like it's it's the faces of the same coin. You know.
You will go to the.
I will go to the primal. All right, so number of decision variables is S for V, and then you have S times S cardinality for the constraints. And then once you find V star, there's an easy way to go to the policy. You just go over all these actions and you get the policy. And then I have this weighting 1 minus gamma because the dual of this dual, which will be the primal, so that the occupancy measures that you end up getting live in a simplex. Okay, and here this is the primal, the dual of the dual. Here you have an occupancy, state action occupancy variable, and you have this constraint that ensures it's a valid occupancy measure. All right. Now, so the number of decision variables change. The way I did the weighting in the dual lambda is not only non-negative, but it's also on the syntax. Okay. So detour finished. We have survived. So we have a dual LP for RL. We have a primal LP for RL. And here you end up solving for, let's say, the value function or the occupancy measure from which you obtain a policy. So far, so good?
So it's this lambdas have this occupancy differential.
That is correct. That is
Also
correct.
time it doesn't.
That is correct. I'm gonna talk a little bit more about this. The imitation learning goal, on the other hand, is that we would like to learn an epsilon optimal policy using as few resources as possible. And this involves now two things for me to explain. One is the epsilon optimality, right? So for this, you can use two definitions. One is that, so suppose there exists a true Lord function, and that you have the value corresponding to the expert policy. So somehow you would like to get close to this within an epsilon in terms of this objective. Yeah? Or we can use the primal definition. Suppose there exists a true reward again. Yeah? And what you would like to do is you want to make sure that the policy that you find somehow matches the expert occupancy measure. So that's what I mean by epsilon optimal policy. We're going to focus on the second one over the occupancy measures. Now we need to figure out the resources. To find this policy, we need to extend some resources. What are those resources, right? One is the expert demonstrations, right? So the expert might be expensive. You don't want to have as many expert samples. Online interactions. So, you know, if you want to do on policy checks, maybe, you know, you want to decrease your sample complexity because, you know, sampling or on policy evaluation will be expensive. And of course, the computation, right? You need to expand some compute in order to find a solution. Okay, now, so let's get to it. The way things are defined so far, we're going to be living in this convex realm. All right, so suppose, you know, from the expert, you have a data set. So you can form the empirical, there's a chalk maybe here.
Yes, here it is. On the blue.
Oh, fantastic. So if you think about it, the expert occupancy measure, it's a distribution, right? But what you have are samples, so the empirical measure. I mean, if you think about it, you know, you have, let's say, a measure like this. So this will be our lambda. But lambda hat are like the samples sampled with respect to it. So in this particular case, and this is like an eye exam at this lighting. So if you can see it in the back, congratulations, you've got very good eyesight. So you end up having more demonstrations here and fewer when the probabilities go down, right? So that's what I mean here. You take these state action pairs and it's as if you have one demonstration there, right? So you just count the demonstrations at that state action pairs. Okay. Now, let's assume that the true reward lives in some set calligraphic art. All right. In this case, you can actually do the following. All right. So I'm going to use a trivial trick. So lambda pi e minus lambda hat plus lambda hat minus lambda inner product with R true. And then I'm going to upper bound this by taking maximum over R, where R lives in this set. Since we assume that the R true lives in the set and this R maximizes, it's like a nice upper bound to it. Yeah. Okay. So then here we have this upper bound. This is something somehow we cannot control, right? Whatever this is, so whatever this R is, it's in some bounded domain. And what we're doing is we're approximating this continuous measure with an empirical measure. So ideally, the more sample you have, the better you are in getting closer to it. And hence, somehow you can upper bound this by the diameter dimension of the problem, divided by the square root of the number of expert demonstrations. So this gives you an idea about the second term. But the first term seems like it's something we can optimize. Yeah? Because if you think about it, you can try to find the occupancy measure that will minimize the worst case deviation. Yeah? And in fact, if you think about it, this is like a dual distance, right? So if you want to write like a Wasserstein distance, for example, this would be something similar, right? Between empirical measure and the true measure. Here, this maximization over a bounded set R with the inner product, you're literally trying to figure out a distance between an empirical measure and another measure defined by lambda. So far, so good? Yeah?
So there is also a notion of this discounted occupancy, right? So in your case, this lambda, whatever you're defining, seems to be like as any extent it will converge to the stationary distribution under that market. So does the discount factor not affect this definition?
So in this definition, it doesn't, but I mean, you are right? There is the discounted factor, but in our calculations, we're going to stick to this one. So we can minimize this distance. And of course, what we need to do is make sure that lambda is a proper occupancy measure. So we need to keep the constraint we had in the primal, or depending on how you look at it, the dual FP formulation. And this will be our problem. So far, so good? Okay. Now, in order to handle maybe, let's say, a little bit larger state action pairs, I'm going to make an assumption, yeah? Right now, I'm not assuming the expert policy is helping. Other questions?
What is the measure constraint on the lambda? The constraint that you make it
You mean the simplex constraint here? I mean, the way we formulated the problem, normally you directly had it. Like this constraint kind of ensures that it is on the simplex. Okay, so this is the initial distribution, this is the state transition, right? And this one just sums up all the actions. All right? So far, so good. Okay, so I'm going to make an assumption. So if you think about, you know, this value function, Q function, and whatnot, when you have them all independent, you can literally put anything in, like you can just put noise, they will model it. But in real life, many of the value functions, nearby states have correlated, smooth, let's say, behavior, and you can encode that with various assumptions. You can put a neural network, you can put something. But this linear MDP assumption is something interesting. We're going to stick with it for this presentation. Okay, we're going to take the linear MDP assumption here. So we're going to assume that the reward at state action pair can be written as a weighted sum of features. Yeah. And then for the state transition, we're going to assume that there exists a function G where you can write this state transition as this feature inner product with this G of S phi. Now we're just going to make these, we're going to use a matrix notation here. So we're going to have a matrix phi, which when you multiply with the weights is going to give you the reward. And for the state transition, we're going to have a matrix phi multiplied with another matrix n. Yes.
Are these very strong assumptions to make?
They are very strong assumptions.
I mean, in the sense, like, usually you say, okay, well, it may not hold in practice, but I'll project them so that the projection satisfies these things.
All right. So you can actually prove that the results that you get somehow gracefully adapts to the mismatches in the modeling. Yes. There exists. Yes. So I covered in lecture 2 of my class. Class. Okay, so this is maybe like an assumption by intimidation. It is standard in the RL literature, so you should accept it, you know. Okay, so we're going to assume that feature mapping is known, but, you know, W and M are unknown. Okay, very good. Now, so we're going to derive this algorithm. But what we're going to do is we're going to try to do this model free, meaning that you're going to assume that we don't know that matrix M. So we don't know the state transition. We're going to use the samples in order to get this. Right? Good. So here's our problem. I just substituted for the reward 5 times W. W is unknown. So the optimization becomes W is in subset algorithm W. And then we have our constraints, and notice that P transpose is now M transpose phi transpose. So far, so good. All right, now we're going to take the adjoint here, and then we're going to use phi transpose lambda as a separate variable law. And we're going to make a split here. So M transpose rho, phi transpose, I mean, you can just plug this back in. The reason why we do this is actually when you develop an algorithm with this splitting, you can do sampling and estimate the quantities of interest. Now, question, who wants to hear how we derive the algorithm? or I just go to the algorithm. So here's the algorithm, right? Or we can talk about how we derive the algorithm. So who says option A, let's derive the algorithm? Option B, who says let's just continue with the the algorithm? Okay, so maybe the winner takes all. We're gonna briefly talk about. So okay, I will be quick. All right. So for this, I just need to introduce what is known as a pregnant divergence. So what we're gonna do is we're gonna define this proximal point method with a distance generating function omega that generates a distance pregnant distance d omega or divergence. So the method is very simple, right? You take a function f of x, you regularize it with this distance centered at the point xk, and you iterate. This is a hypothesized algorithm. Typically, solving this is as difficult as minimizing f itself. But when f is linear, magical things happen, okay? So for example, when you take omega as this x log x, it gives the KL divergence, and the updates here, for example, if you have the linear, it'll give you these exponentiated entropy mirror type of updates that are very advantageous in terms of optimization because it gives you like logarithmic dimension dependence. All right, ready? Okay, so given the linear objective and the linearly constrained problem, you introduce Lagrange variables and go to this minimax form. All right. So we're minimizing with respect to rho lambda, maximizing with respect to W. And I think the theta should be the dual variables, yes. And V is the additional dual variable. So you have this whole linear term. Okay. So what we do, because this is linear, we're just gonna do proximal point on this linear update, given a center point, which is the previous occupancy measure by transpose and the occupancy measure, and we're gonna use the relative entropy and the conditional relative entropy in their respective spaces. And here, we're gonna do normally a crime, but in the convex concave cases, this is not, right? We're going to swap the min and the max. And it turns out that when you do this swapping, you get this inner minimization problem, which is analytic updates. Right? You just get this nice exponentiated form immediately. And what we do then is to take the minimizer and plug it in because it's analytic. Now you're going to get a maximizer problem, which turns out to be smooth. Okay. So far so good, right? So here are the maximizers and you plug them in there. And then, okay, so you end up getting this plugged in with the definitions you have done. You end up applying a gradient method to this. So just to repeat, you take analytic updates for the minimizer. For the outer problem, you run a gradient method and you repeat the proximal point method. All right? Yay, we have survived. Okay, so here's the algorithm. You get the analytical updates. Very nice. You solve this with a gradient method inexactly. Does that make sense? And you iterate. So again, just showing this. I'm not sure, this is very helpful, but hopefully. Say it again.
I know what W is. So what's theta?
In this case, actually, so theta turns out to be something like RQ function, right? I mean, so to be honest with you, I'm not doing justice to the formulation, right? When you get into this, it's like an onion. It has many layers, and every layer can make you cry because there are many details and subtleties here that I'm like literally sweeping under the carpet. Okay. All right. Now it turns out that when you do inexact iterations, then there are certain issues that appear, okay? In the sense that if you look at our objective, which we want to do, so you run this inexact gradient method, you average methods, and averaging is okay because we're in the convex realm. Then you can show this distance. So m is the dimension of the weight space, a is the telegraphy a is the action space. So you have a nice log factor. We have this nice one over k convergence, but then there is this growth of the inexactness. Yes. Is theta dependent on w? I mean, what do you mean? It's
W is the parameter of the reward.
w is the parameters of the reward. Yeah.
Theta is the parameter of the.
Theta is, I think, the dual variable, right? Yes, but it is interpreted in the end that way after you do the explicit minimization, right? It comes out like this. So here, what we ended up doing is that we look at the stochastic gradient ascent subroutine, and then we show how this particular error term is controlled as your iterations change. And you know, you have some dependence, you have n the dimension, and then you have square root of t. So let's say you do t iterations. So you have a guarantee like this in terms of accuracy. And then just don't look at this beta. It's don't look at it for the time being. What happens here is that when you choose the number of iterations as epsilon 1 over 1, you choose the inner iterations for epsilon to the minus 4, you obtain an epsilon to the minus 5 online interactions, sorry. You use those samples, you compute these quantities, we handle the bias and so on and so forth in the gradient, and then you have a convergence. I'll give you the final convergence at the end of the talk. Yeah, so there is this data, and we're going to get back to that. All right. So far, so good. All right. Let's just see this in action. So here, this is just some stylized examples people like to use. The curves that you would like, I would like you to notice is IQ learn, which actually has no theory. And it's something like a double smoothing approach. So they literally smooth the maximization with like a Nestor dual smoothing. You get a primal, and you just run an algorithm there. All right. And if you compare to this blue, which is typically on top, is our method. So the next competitor is IQ learn method from Stanford. And now I know that, you know, we haven't done anything with the neural networks, but you can plug in the neural networks for some of the quantities of interest. And this idea still seems to work. All right. Very good. And what is interesting is that you can do offline experiments because in the proximal point method, you have a center point. If you anchor the center point to the expert, you can try to solve this problem. And in that case, you don't need any online sampling. So here there's point, which is somewhat difficult. There's some, you know, you probably know this better than I do, right? It seems to do well, right? So far, what we've done is we've used this linear programming approach to come up with this min-maxing problems. We applied a well-known method. We literally went through the due diligence in characterizing the impact of epsilons. We've got the sample complexities. It looks like for the quantities where, you know, you have, let's say, a reward function and so on and so forth, you can plug in neural networks and so on and so forth. Still seems to work. What is interesting is that as part of this process, we learn a reward, right? Because it's something that you optimize with. But while the reward you get is not similar to the true reward that you use, right? Our algorithm actually returns these. So there's a typo here. This is R true. That seems to be exactly the V star. Yeah. So this was quite surprising to me. We haven't done the analysis for this, but seems very interesting. Right. So the value you get out of this seems to match the value you're seeking. Okay. Very good. Yes.
So one would expect that even though the rewards are different, the ordering of the rewards is what matters. The reward values as such don't matter. So do you think maybe although the rewards RK and R2 are very different, maybe the ordering of the rewards for different actions are more or less similar?
I mean, maybe you should have taken an average reward, you know, at the same time, because the sequence, I don't know, in the minimax case, unless you have certain assumptions, maybe the sequence does not necessarily converge, right? But the average does. So actually, I'm curious, maybe we should have also averaged few. I mean, you know, like if you just apply gradient descent ascent to a simple bilinear problem, right? The sequence will just cycle around, but the average will converge to a min-max point. So now that I think about it, maybe we should have done something like this here too, right? So I'll actually look at this. All right. How are we doing? Good? Okay. Now, so we started with the stylized, let's say, linear programming. We made an assumption, which was already strong to begin with, right? Linear MDP. And we made another assumption. So there was this beta in the denominator, right? Do you remember? People remember that beta? So it turns out that that beta is an assumption that says something like this. So the algorithm generates some policies, right? And all these policies should visit all state action pairs with positive probability. So the strength of the assumptions is like Mount Everest now, right? So you look at some feature covariance and it's lower bounded by that beta, and that actually implies that all the policies generated by the algorithm will visit all state action pairs. But in many problems, this many state action pairs should be avoided, right? So this seems like it's not good, yeah? So this is what we're gonna do now, right? We're gonna, in the next 15 minutes, let's say, we're gonna talk about how to avoid this assumption. Okay, so let's remember what we want to do. We want to get this absolute policy using as few resources as possible, right? So this is like Groundhog Day movie, right? So we've gone through the day and we realize we've done something terrible. We just wake up remembering that. So we're gonna do the same thing again, but with a different approach. So here's our optimality condition, right? Deja vu. We're gonna focus on the second one, deja vu again, right? But what we're gonna do is we're gonna copy Praneeth, right? I don't know if he's still here, but we're gonna copy Praneeth. We're gonna do online optimization. What we're gonna do is we're gonna view this particular term as a regret term. All right. Good. So we're going to use online learning to optimize this regret. And what we need to do is somehow overcome the fact that because we do not know R2, we cannot do a regret analysis. Do you see this? Right? There's the fixed point in which you're taking the regret is not known. Okay. Good. So just to set up the notation, and I'm glad that, I mean, for those of you who've been in Praneeth's presentation, will remember this. So here's the standard setting for online optimization in my notation. So a learner faces a non-stationary environment for k hours. What do? We play a decision in some convex set X. The environment will choose a loss vector, and then we're going to suffer a cost, which is the standard product. All right. And then we're going to observe the loss. Okay? So, I mean, there are slight variations. You can observe the cost in the bandit setting, but we're going to observe the loss. All right? Good. So we're going to define the regret as a summation of these losses with xk, but we're going to have another point x star here, which is called a comparator. Pradeep also mentioned this, right? Typically, the way you choose the comparator is that you put a max here and then say x maximizes this regret. But we're going to keep this floating for the time being. We're going to keep the comparator not constant. So what are we going to do? So we're going to take another trivial decomposition. So we're going to add and subtract RK. We have one term, two terms, and their summation needs to be less than or equal to epsilon for our optimality. So far, so good. And what we're going to do is we're going to set up a game between two players. One will be a policy player, the other one will be a reward player. Okay, so this is, I mean, if you think about it, this is like a collaborative game, right? Because they both want to go under epsilon. But at the same time, it has all the dynamics of a game, right? One going higher means the other one has to go even lower. So there will be a policy player that will update the policy, and there will be a reward player that will update the reward, right? And what we're going to do is we're going to try to generate sequences IK and RK so that they both have sublinear regret. Normally, what we do in the pi2.il is that we directly get the worst case R. What we're going to do now is we're going to update them with the information we observed online while doing the experiments. Make sense? Okay, good. So let me twist things around so that the regret definitions are clear. So somehow the regret for the reward player is R2. And the regret for the policy player is phi e. Yeah, we're doing minimizations with respect to the regret, so this is minus R by our loss. Yeah, and for this, it's the difference between the occupancy measure of pi k and the occupancy measure of the extra. So far, so good. Now, question. Should we derive the algorithm or directly go to the algorithm? I told you, right? Groundhog Day. So who says, let's just look at the derivation? No interest this time? Okay, so people don't want to? I'm happy to take the questions offline, but I think given the time, I should be able to quickly go over the derivation, to be honest with you. So...
Groundhog Day.
Huh?
Groundhog Day. So you...
Oh, Groundhog Day. Okay, so let's do it. Let's do it really quick, really quick. I'll be quick. Okay. So for the reward player, things are good and dandy, right? Like you just apply online gradient ascent, no problem. You have unbiased estimates. You can just do certain things. Okay, so there are certain things that cannot be computed, but what you do is you take the regret, you end up having a decomposition. Some of the elements of this decomposition are known, right? People know how to get the quantities in. And okay, so let me stick to my word. I'm not going to get into too many details. So some of these terms telescope, other ones slowly vary, and you can actually get a nice analysis. But the key thing here is this, all right? What you end up doing is you try to get an uncertainty estimate on your, let's say the transition applied to VK. You want to get some idea about the uncertainty in certain state action pairs. And the analysis is actually cool in the sense that without assuming exploration assumption, you end up separating the cases into two, where if the uncertainty was high, you go and so if the probability was high, you go to a state. If the probability was low, you don't go to that state, and that state turns out to be not important for any of the terms that you're interested in. So you don't need to go to the states that are unimportant. You don't need to visit all states. Their probability is so low that does not affect your regret. That's the key takeaway. So we can prove that with some standard updates and sampling in online gradient ascent, you get sublinear regret. Okay, so here's the algorithm. There's the reward player update. There's the policy players update. There's some estimate of the probabilities for the state action pairs. And you have your usual analytic updates. And if you remember, IQ-learn was below P squared I. P squared I was above, and the new algorithms, adversarial imitation learning via adversarial training, adversarial area, it's the one on top. It seems to work really, really well. Okay, so let's do the literature comparison. There's quite a bit of algorithms, and many of them are, I don't know, so coming or derived from intuition. What we've done is that we came up with a framework, this proximal point imitation learning, that has a sample complexity bound. It actually has quite good empirical performance, and just because it's like standard optimization, we know how to do the step size selection. You do graduate student on it, right? Sorry. For the step sizes, you use what is known as a graduate student descent. So until it works, you put more graduate students on it, and it makes it work. Yeah. So for the adversarial learning, we have theoretical guarantees, and I'm going to summarize them in the next slide. For the stylized examples, it works the best, right? Like it really outperforms anything we've seen, and we're currently doing the neural network version of it. Okay, so again, this is a high exam. So if you can see this, again, congratulations. So proximal point one actually had the best sample complexity results, but this regret minimization approach seems to even make that better. In particular, the dimension dependencies go better, the epsilon dependencies go better. All right, good. So I'm just going to do a side note before concluding. So far, the analysis with the linear function, linear MDPs. I think that the theoretical analysis for deep neural networks is difficult here, though we managed to make some analysis for deep neural networks. What we did is we assumed that a Q function belongs to a Bezos space or a Barron space. And then we use the least square value iteration and show that with a certain scaling of the width and the depth, you can actually get a good approximation of these Q functions by using deep neural networks. Yeah. So that's like a side note if you are interested in that kind of analysis. But let's conclude. So I think that this optimization perspective provides a very interesting approach to, let's say, imitation learning. In the first half, we did what is known as offline optimization, in the sense that we came up with this minimax formulation, we applied proximal point to it, right? And then everything is worst case, right? You take the reward, it's maximized everything in worst case. In the second half, we looked into the problem as an online problem. So as opposed to taking things the worst case, we adapted to it, and that enabled us to get even further improvements in the theory and also in practice as well, right? So with that, I will end. If you have any questions, I'll take them.
Questions for Vulcan? Gugan?
So what are the kind of assumptions on the expert that you make? So you have this 5E and all those things. So who is an expert?
So expert could be very bad, right? We're talking about approximating the expert. So expert is a valid occupancy measure. Because we give a guarantee in such a way that we're going to come up with a policy that will generate an occupancy measure that will match the expert's occupancy measure. We didn't say that the expert is optimal with respect to some function and so on. So on.
I think you have a question.
That is very
It could help, yeah.
So at some point you said that you don't want to visit every state and action. Right?
In
But-
general, yeah. No, you don't want to have a condition that says the sequences that you generate should be such that every policy should have a non-zero probability of stating visiting any state action pairs, right? But with the regret one, when you're characterizing, you end up having these regret terms, and there's like a Farkas lemma kind of. You put them into two buckets, right? If it is important, you visit. If its probability is so low, then you don't, and it will not affect the regret that you have.
But did you not in the previous slide talk about an epsilon greedy algorithm? So in there, if you fix an epsilon, wouldn't be forced to visit every.
We didn't do epsilon greedy, no.
But in the
It's not epsilon greedy, right? It's the way you go from the value to the policies. Once you have the optimal value function, you can take the greedy policy there. It's not epsilon greedy. It's the greedy policy with respect to the actions when you have the correct value function. Through Bellman equation, you get the optimal policy directly, yeah? It's not the same.
Just a quick question. I wanted to understand the role of the Bregman divergence, specific Bregman divergence,
yeah.
and how it affects the outcomes. So can you tell something?
Thank you for this question. The Bregman function plays a key role. So if you look at the previous presentation, discussed minimization problems, and in particular when you use, for example, let's say Krasnoselski man iteration or the inertial version and convergence to minimization. With the Bregman iterations there, depending on the constraints that you have, you get things like dimension dependent improvements in your convergences. So if you have a simplex constraint and you use the entropy, so if you use this x log x as a distance generating function, you end up getting updates where you don't need to worry about the constraints anymore. The updates directly give you the results, and you get logarithmic dependencies on the constraints. And what we've done in the previous setting is that we characterize the mirrored descent type algorithms, including extra gradient, optimistic gradient, or single point approximation, 2-point approximation, or the bandit settings, using the mirror descent template in the general mini-map settings. So the convergence theorems, etc., we saw in the previous presentation, we've done it for minimax. For this, it gives you the dimension improvements.
The question is specifically, how do you go about choosing the Bregman divergence? I think when you use the x log x, you have all these nice properties.
Yeah, for the simplex, there exists a distance. So there's an existence results for finding mirror maps. So for any convex set, there exists a mirror map that will do the same thing. But constructing those mirror maps is actually quite difficult. Though there is a paper by Ian Tatley and Aaron Sitford that does this for a restricted set of convex sets, from my knowledge.
Computation of the minimum is also an issue, which if
That
it
is correct. That is correct.
Any other questions? Yeah.
So the plots that you have shown, what is the
Expert policy is in the data set from what I remember. to be honest with you, don't ask me about the exact settings of the experiments.
What was the metric that? Zero to one?
So actually, this was this is great. So the expert achieves a certain reward, and what we were measuring is the reward that our learned policy achieves, right? And what is funny is that you see, for example, one. So one is relative to the expert, right? So the value one is what the expert achieves, and sometimes we go above it in the environment. That was interesting.
What gain you get when you formulate as a manual dual problem?
What is the game I get?
Gain.
Oh, so when you write it in terms of, let's say, primal dual minimax problems, if it is in the, let's say, if you don't do neural networks and so on and so forth, you have this strong duality, right? There's this nice relationship that you can exploit between occupancy measures, value functions, how you go between them, and you end up writing, you can just stand on the shoulders of giants, right? You can apply various algorithms if you formulate them in the Lagrangian, which is in between. You can apply extra gradient methods, you can apply proximal point method. That's the reason why I like this, because there's like a host of algorithms you can just bring in from game theory, and regret analysis as well, right? Similarly.
Let's thank Volkan again for his fantastic talk. Token of our appreciation for Volkan, we have the Secret Lives book. This has fauna of the Indian Institute of Science, pictures of those. It's been taken by a grad student who graduated out of it. Thank you very much.
Thank you very much.